Previously, we examined the case of a free particle. We now turn to a more interesting and complex scenario in which the particle encounters an obstacle. One of the simplest forms of an obstacle is a step potential. As before, we consider a one-dimensional space represented by the x-axis. However, this time we assume the potential is constant for x less than 0, and x greater than 0, but discontinuous at x equal to 0. More precisely, we assume the potential is 0 for x less than 0 and has a constant value of v sub 0 for x greater than 0. When the particle crosses the point at x equal to 0, it experiences a sudden kick. This kick is directed to the left if v sub 0 is positive, and to the right if v sub 0 is negative. Now, imagine a quantum particle initially localized on the left, and moving toward the potential step. Our aim is to analyze this scattering scenario by predicting the particle's wave function during and after its interaction with the step. Let's first recall how we would construct the particle's wave function in the free particle case, which corresponds to setting v sub 0 to 0. The wave function is given by this integral over k. As we've previously seen with Gaussian wave packets, k is closely related to the particle's momentum. In fact, the function phi of k determines the particle's momentum distribution. Therefore, we restrict the k integration range to positive values, as only these are needed to represent a wave packet moving from left to right. The primary focus of our current discussion is the spatial part of the integrand, specifically the complex exponential term, commonly referred to as a plane wave. Recall that this plane wave was derived as the solution to the time-independent Schrödinger equation, which can be written in this form. Here, k is proportional to the square root of the energy E, which appears in the Schrödinger equation in its standard form. In the scattering case, when v sub 0 is non-zero, the particle's wave function is given by a similar integral over k. The only difference from the free particle case is that now the spatial part of the integrand, denoted by lowercase psi of x, is the solution to the time-independent Schrödinger equation that accounts for the potential function v of x. So, to predict the particle's wave function during and after its interaction with the potential step, we need to solve the last equation. The obtained solution can then be fed into the integral, which can be evaluated, analytically or numerically, to yield the particle's wave function psi. The exercises accompanying this lesson will guide you through the process of solving the time-independent Schrödinger equation for the step potential. Here, I will only highlight the key points. In solving the equation, we need to consider two different cases separately: when the particle's energy E is smaller than the potential step v sub 0, and when E is greater than v sub 0. The first case can be schematically illustrated like this, with the red dashed line representing energy E. To the left of the step, the potential function v is 0, and the Schrödinger equation takes its free particle form. In this region, the solution is a linear combination of two plane waves, e to the power ikx, and e to the power minus ikx, respectively representing the incoming and reflected waves. The relative complex valued amplitude of the reflected wave is denoted by b. Of course, plane waves and their linear combinations are generally complex valued functions. Therefore, the red curve sketched here is not an accurate representation of the function psi. You can think of this curve as representing, for example, the real part of psi. As you will see when working through the exercises, the solution of the Schrödinger equation to the right of the step takes the form of a decaying exponential. The complex valued amplitude of this exponential is denoted by c, and the decay rate, k', is given by this expression. The two amplitudes, b and c, are determined by ensuring that the left half of the function psi joins smoothly with the right half. Mathematically speaking, this means that the function psi must be continuous and differentiable at x equal to 0. As you will establish while working through the exercises, these continuity and differentiability conditions, commonly referred to as matching conditions, yield the following values for the amplitudes. Let me draw your attention to the following. The fact that the amplitude c is generally non-zero means that the wave function of a particle with energy E smaller than the potential step can actually penetrate the step. Classically, this would be impossible, as the potential energy of a particle cannot exceed its total energy. This counterintuitive behavior of quantum particles is known as quantum tunneling. We will explore this fascinating phenomenon in greater detail in the final part of this course. Now, let's consider the case where the particle's energy E is larger than the potential step V sub 0. As before, for x smaller than 0, the function psi is described by the free particle Schrödinger equation. The solution is, once again, a linear combination of two plane waves, the incoming wave and the reflected wave. The yet unknown amplitude of the reflected wave is denoted by b. For x greater than 0, we have only the transmitted plane wave, e to the power ik double prime x. As you will see when working through the exercises, the wave vector k double prime is determined by the difference between the total energy E and the step height V sub 0. The amplitude of the transmitted wave is denoted by c. As before, the amplitudes of the reflected and transmitted waves, b and c, are determined by the requirement that the function psi must be continuous and differentiable at x equal to 0. These matching conditions lead to the following expressions for b and c. We now have the explicit form of the function lowercase psi, for any value of k, which can be substituted into the k integral above. By selecting the momentum function phi of k, such that the initial wave function psi is a Gaussian packet approaching a potential step from the left, we can calculate the particle's wave function during and after its interaction with the step. Let me show you the results of this calculation for various system configurations. First, let's consider the case when V sub 0 is positive, meaning that the particle receives a kick to the left as it crosses the origin. You can see that the initial wave packet splits into two parts, representing the possibilities of reflection and transmission. Second, let's consider the case when V sub 0 is negative, meaning the kick is directed to the right. In classical mechanics, such a kick would simply accelerate the particle, without changing its direction of motion. However, in the quantum mechanical case, we see that a downward potential step can also cause the particle to reflect. The final, and most surprising scenario, occurs when V sub 0 tends to negative infinity. Physically, this represents a particle approaching a steep downward cliff. A classical particle would simply fall off the cliff. Counterintuitively, the quantum particle is completely reflected by the cliff instead of falling off. This intriguing phenomenon is known as quantum reflection.